Do subscribe to Ekeeda channel and press bell icon to get updates about latest engineering, HSC and IIT JEE main and advanced videos.
The arithmetic and logical instructions, they are used to perform the arithmetic and logical operations like addition, subtraction, logical and, logical or, compare, increment, decrement. So whenever these operations are to be performed in 8086, these instructions are used. So let us start with our first instruction, which is used for addition, that is add. The mnemonic of this instruction addition is ADD. So whenever we want to use this instruction, we are going to write ADD add in the main program. So this add instruction, it is used to add the contents of the destination and the source, and the result of this addition, it is stored in the destination. Okay. Here we can use the source and destination. It can be the registers also, it can be an immediate data also, it can be a memory location also. When this instruction, add instruction, it is used, then all the flags like carry, auxiliary carry, sign, parity, zero, overflow, all these flags are affected. So we can say that all the flags are modified, and we can check the status of the result in these flags, that if in the case of addition any carry is generated, if the addition has generated a zero, then how many number of ones are there. So we can check all the flags will be affected through this instruction. Let us take an example. If we talk about the general format of this instruction, then generally it is written as add, then destination is written, and then source is specified. So source is added with the destination and result is stored in the destination itself. Let's take examples. This is an example where an 8-bit data is added with the contents of the AL register. AL is the lower order accumulator register. So this register is also an 8-bit register. So the contents of this register are added with this immediate data 0FH, and the result is stored in the AL register only. This add AX comma BX, this instruction, it is going to add the contents of the BX register and the AX register, and result will be stored in the AX, because if we compare it with this, then destination is AX and source is the BX. So result is going to stored in the destination. Okay. AX and BX both are 16-bit registers, so the result will be also a 16-bit or more than it can also be generated. Okay, so 16-bit numbers are added. Here we are adding the 8-bit numbers. Now this is an example where we are adding the contents of the AX register with the memory location, and the address of that memory location is calculated by adding the data segment with the source index register. Okay, so the address will be data segment multiplied with 10h plus the source index. So that will be the address of the memory location, and at that memory location the data is stored. So that data will be added up with the accumulator register and result is stored in accumulator. Okay. Suppose this type of instruction is written add 0100h. So here the operand, it is specified in the instruction itself. The operand is implicit here. So this is a type of implicit addressing. Here by default we use the destination register as the accumulator. So one of the operand will be accumulator. Its contents are added with this data 0100 and the result will be stored in the accumulator itself. So when we are not specifying the operand in the instruction, that type of addressing mode is called the implicit addressing mode. So this is the addition add instruction through which we are adding the contents of either two registers or register and a memory location or an immediate data with the register or the memory location. Okay. Next we have the addition with carry. We are using the carry flag here, and this carry flag along with the data, it will be added with the contents of the destination. The mnemonic for this instruction is ADC. We are going to write ADC in the main program to use this instruction. So this is adding the contents along with the carry. So this ADC instruction, it also performs the addition operation, but it also adds the carry flag bit to the result. Now this carry flag bit, it may be set or reset due to some previous instructions which are executed. So that carry flag bit, if it is 1 or 0, then that bit will be added to the destination along with the source contents, and the result will be stored in the destination. Also, all the flags are affected due to this instruction. The carry flag, parity flag, all the flags will be affected. Now, if we take the examples, so here we are writing the mnemonic ADC and we are adding the contents of AX and BX register along with the carry flag. Here AX and the address of the memory location which is obtained by adding the data segment and the source index. That memory location, that data plus the accumulator register and the carry flag. Then here we have the address of the memory location, data segment plus this 5000. So that memory location data is stored there. That data will be added with the AX register and plus the carry flag, and result is stored in the AX. Here accumulator, carry flag and this data, it will be added and a result will be stored in the accumulator. So these are the examples of the add with carry instruction. Next instruction we have is for the subtraction, SUB. The mnemonic for this, the code is SUB. We are going to write SUB to use this instruction in the main program. So this instruction, it is used to subtract the contents of the destination with that of the source and store the result in the destination. So destination will be subtracted from the source and result is stored in the destination. Through this instruction also, all the flags will be modified. So let us see the examples of this instruction, SUB. If we talk about its general format, then we will write SUB, destination and source. So we can have SUB, so these are the examples of this instruction. In this, the 0F data that is subtracted from the AL, that is the lower order register of the accumulator, that will be subtracted and the result is stored in the AL register. Here BX is subtracted from the AX, that is AX minus BX is executed. Here the contents of the memory location, they are subtracted from the AX register contents. Here this data is subtracted, the data at this memory location, it will be subtracted from the AX register. So these are some of the examples of the subtraction. Okay. Next instruction we have is subtraction with borrow. Just like we are having the addition with carry, then we are having here the subtraction with borrow. Okay. For this we will write the mnemonic SBB, that is subtract with borrow. So when we are using this instruction subtraction with borrow, means we are subtracting the source operand and the borrow flag. Borrow flag means the carry flag. Carry flag, it is used as both the for addition and for subtraction also. In case of subtraction, it is treated as the borrow flag. So borrow flag is just the carry flag, and we are subtracting the source and this flag with the destination. Okay. This means that we are subtracting 1 from the subtraction which is obtained by this SUB instruction. So the subtraction is the same, but we are subtracting 1 also from this through this SBB instruction. Examples of this instruction are So examples are like the same. We are writing here the SBB instead of SUB, and we are subtracting this content plus the borrow flag with this accumulator register. Also here the BX register, borrow flag with the from the AX register. Okay. Here also all the flags will be modified and the result of this operation will be stored in the destination. Next instruction we have is the compare. For this instruction we have the mnemonic CMP. So we are going to write CMP in the main program to use this instruction. Now this instruction, it is used to compare the contents of two registers, like whether these two contents they are equal to each other or they are greater than or less than each other. So this comparison is done using this instruction. So this instruction compare, it is going to compare the source operand, which can be a register or an immediate data or a memory location, with the destination operand, which can be a register or a memory location. So in comparison, it is going to compare the source and the destination by subtraction. So this comparison is done by subtracting the source operand from the destination, and the result of this subtraction, it is not stored anywhere, just the carry flags, the flags are checked. Suppose if the source and the destination they are equal to each other, so when they are subtracted, then zero flag will be set, because the result of the subtraction will be a zero, because both are equal, so zero flag will be set. So if both source and destination they are equal, then zero flag is set. If suppose source is greater than the destination, then carry flag is set, means it will be equals to 1. And if source is less than the destination, then carry flag is reset, means it will be 0. So this comparison is done by checking the 0 and the carry flags. If they are set or reset, then the interpretations are made that whether the contents are equal to each other or they are greater than or less than to each other. So let's take some of the examples of this compare instruction. So these two instructions are an example of immediate addressing, where the immediate data it is available in the instruction itself, and this data is going to be compared with the BX register. So these two operands they will be subtracted from each other, and then the zero flag and the carry flag they will be checked. We have some other examples of this instruction also, where the contents of this BX register and the address of the memory location, which is specified by the source index, plus the data segment, that memory location is having the data, so that data will be compared with the BX. Here the contents of the BX and CX registers are compared. So these are some of the examples of the compare instruction. Next instructions we have are the increment and decrement instructions. These instructions are used to increment or decrement the contents of the registers. These instructions, they also affect all the flags, auxiliary carry, all the flags are modified. Example of these instructions are these INC AL and INC AX, they are going to add the lower order register, accumulator register. So AL plus 1 will be done and the result will be stored in the AL register. So this will be incremented by 1. Then AX register, it is also incremented by 1. Through this DEC, decrement is done. So AL will be decremented by 1 on AX is decremented by 1. So these instructions are used to increment or decrement the contents of the specified destination. Next we have the logical instructions like logical AND, OR, XOR, NOT. All these logical operations can also be performed through 8086. First we have the AND instruction. This instruction, it is going to AND the contents of the source and the destination, and the result is stored in the destination. Okay. Now here every bit of the source and operand and the destination, they are going to be ANDed with each other. So this AND instruction, it is going to logically AND each bit of the source byte and word with the corresponding bit of the destination. So suppose the source is having an 8-bit data and that 8-bit data is having the bits from D0 to D7. The destination is also having an 8-bit data from D0 to D7. So every bit will be ANDed with each other. D0 of source will be ANDed with the D0 bit of the destination. Similarly, D7 will be ANDed with the D7 bit of the destination. So corresponding bits, they will be ANDed with each other and the result of this operation is stored in the destination. Here the carry flag and the overflow flag, they are set to 0, and the 0 flag, parity flag, sign flag, they will be affected, and auxiliary carry flag, it is undefined. If we see the general format of this instruction, then we have this AND, then destination, and then source. So the destination and source, they are specified in the instruction and their bits will be ANDed with each other. Let's take some examples. And BL and AL registers. Both these registers are 8-bit registers. Suppose BL is having the content this and AL is having, then both these bits, the registers bits, they will be ANDed with each other. So we will get this result of this operation will be stored in the BL register. So each bit, you can see that each bit is ANDed with each other and the corresponding result is obtained. Okay. Just like this was an 8-bit AND operation. Here we can have CX and AX. Both are 16 bits, so we can have the 16-bit AND operation also. So the contents of CX are ANDed with the contents of the AX register. Now this was the example of the AND instruction. Next we have is the logical OR instruction, where the OR operation is performed between the source and the destination. Mnemonic is OR. So this is also going to logically OR each bit of the source and the destination. Here flags are also modified just like the logical AND. We are going to set the carry flag and the overflow flag are made to 0. 0 flag, parity flag, sign flag, they will be affected, and auxiliary carry flag, it is undefined. So if we take the examples, its general format will be, we are going to write the OR instruction, then we will write the destination and then source. So if we take the examples, we have OR BL, AL. So suppose BL is having the 8-bit data as 10000110. AL is having the data so these two registers, they will be logically ORed with each other. So we will have 1100 and 1110. This will be the result of this operation and it will be stored in the BL register. Also we can have OR CX, AX. So these two 16-bit register, they can also be logically ORed with each other. So corresponding bits of the source and the destination, they are logically ORed and the result of this operation is stored in the destination register. Next instruction we have is the NOT instruction. This instruction is going to complement the bits of the register which is specified in the instruction. Complement means that if its bit is 1, then it will be made 0. If it is 0, then it will be made 1. Okay. Complements, or we can say invert the contents of an operand. This operand can be a memory location or a register. So its format will be like NOT and we are going to write here the operand. If we take examples of this instruction, NOT AX. So AX is a 16-bit register. Suppose its contents are, this was the content, it was a 16-bit, so we can write here, suppose this was the content. When this operation is performed, so AX new contents will be so 1 is changed to 0 and 0 is changed to 1. So these are the new contents of the AX register after applying this instruction NOT. Next instruction we have is the Zuhr instruction. This instruction is going to perform the logical XOR operation between the source and the destination. So logical XOR operation, it says that when the two bits of the source and the operand, they are dissimilar to each other, then we will get a high on the output. Okay, so if we take 0 0 0 1 1 0 and 1 1, then 0 0 will produce 0, 1 1 will also produce 0. When the two bits are dissimilar to each other, then we will get a high at the output. So in this way, the bits of the source and the operands, they will be checked. When both the bits are dissimilar to each other, then in the result we will get high, that means 1, and if the bits are similar to each other, then we will get a 0. If we take an example, XOR AX, 0098H. So this is the immediate data, and this will be compared with the contents of the AX register. So both will be logically XORed with each other, and the result of the operation will be stored in the accumulator register. So suppose that the AX, it is having the contents These are the contents of the AX register. It is a 16-bit register. Now we are having 0098. So 0, 0, 9 and 8. We are going to logically OR this, XOR this. So 1 0, the bits are dissimilar, so we will get 1. 0 0, bits are similar, we are going to get 0. 1 0, dissimilar. 1 1, similar. Similar. So this will be the result of this operation, and it will be stored in the AX register. So this was the logical XOR operation. We are going to write XOR and the destination and source. Okay. So we have studied about the logical instructions which are available in the 8086 microprocessor instruction set. We studied the arithmetic and logical instructions, like in arithmetic we studied addition, subtraction, addition with carry, subtraction with borrow, and increment, decrement, compare. In logical we studied the logical AND, OR, and XOR and NOT operations. So in this video we studied about all the arithmetic and logical instructions which are available in the instruction set of 8086 microprocessor. I hope that this topic is clear to you. Thank you.